All right, everybody, 2 o'clock. Welcome back to your favorite class. Yes. My theory is if I keep saying that, you'll actually believe it, right? It's very like, well, I don't want to be politically incorrect, but very Trumpian of me. If I just say it a bunch, maybe you'll think it's true. Okay. So let's get back to business. I did post your first homework as advertised yesterday. That's going to be due on Tuesday to my email inbox by the beginning of class. And that'll be on some of the vector math that we've kind of talked about this week. So visit the Canvas website, take a look at that. It's only 4 problems, I think relatively simplistic ideas since we're just talking about vector math now, which is something a lot of you have probably seen before, so shouldn't be that bad. Okay, due next Tuesday at the beginning of class. Again, if you're struggling and you have questions, I have office hours every single day, 8 to 9:30 a.m. on Teams. Send me a message and we'll work it out. All right, so with that, I thought we would continue where we sort of left off. And just to refresh where we were last time, I'll just kind of show my notes here where we were. We had finished off with this example problem looking at adding 2 vectors together to get a certain resultant. We talked about particles, what they are, what they represent. We talked about forces, line of actions. Forces are vectors that have magnitude and direction, all that good stuff. So we looked at this example problem here where we added 2 forces together. And the first way that I'm sort of introducing how we're adding vectors together is a method you probably learned in your physics class, just like the tip to tail method. Okay, so here we're looking at vectors Q and P. They're added together and we're looking at finding the resultant. And so we went through this example problem by drawing them sort of tip to tail. It's not working. There we go. Okay. By sort of drawing them tip to tail, and we made this sort of diagram to get our resultant force R, which is P plus Q. And we went through a bunch of math using law of sines, law of cosines to determine that the magnitude of the resultant was this 97.7 newtons. And for direction, we used law of sines and showed that it was acting at 35 degrees above the horizontal. All right. Now, that's a nice introductory method, this like tip to tail method. Describing how we can add vectors together. And it's a nice graphical description, but if you have, let's say, 4 or 5 or 6 vectors acting at a point, you don't want to put 4 or 5 or 6 vectors tip to tail and make some heptagonal structure where you have to sort of like connect all the angles together, and that would just be a huge headache. Okay, so yes, the tip to tail method is nice for demonstration purposes, and triangles have nice formulas that can sort of work out and be pretty, but there needs to be an easier way to sort of add these vectors together, and that's what we're going to talk about today. And that has to do with a concept that we're going to dive in on today, which we call unit vectors. And unit vectors were something that when I was in your chair, were not explained very well by the teacher that I had. And so for a while in my statics class, maybe my first 2 weeks or so in my statics class, they kept talking about unit vectors. I was like super confused. Okay, I was like, what is a unit vector? Why is it even useful? I just like wasn't grasping it, like why we had it or why it was important. So I really want to hammer this because it was something that I struggled with when I was your guys' age, and that I think is a really important concept, not only in this class, but in other classes as well. So let's first talk about or dive in on a little more detail of something that we were discussing yesterday, which is resolving a force into various directions. So we'll talk about rectangular components of a force. Okay. And so I'll remind you that we can take whatever force that we have in a 2-dimensional plane and sort of break that up into an infinite number of other vectors that we could then add together to get our original vector. And it might be helpful or useful for us to sort of like break that first force down into a variety of different directions so that we can sort of manipulate them a little bit more easily. And so one technique that we can do is sort of break a vector up into orthogonal directions that can sort of help us on our way. Okay, and so I'll write here that often it helps with analysis to deconstruct a vector into orthogonal components. Okay. And so what do I mean by that? Well, if we have some vector out in space, which is like some vector p, I can break this into some orthogonal components by assigning some random axes in space, usually as you have done since you were like 10 years old. You break this up into like an XY coordinate system. And you can resolve this force P into components that are like along the X direction and along the Y direction. So you might think about resolving this guy into something like Px and Py. Okay? In this situation, since we learned about vector addition yesterday, you could then say that the vector P is a combination of Px plus Py. Okay? And it doesn't necessarily have to be like this XY coordinate system. You could make, any sort of arbitrary coordinate system that you wanted. Sometimes it's useful if you're working on, like, let's say friction problems and you got some box on a plane. Maybe to align your coordinate system with the plane that the box is sliding on, for instance. So yeah, maybe you got some force here, P, but instead of the traditional XY axes, maybe you want like some other axis that looks like this, which might be like a normal and tangential axis. Okay. If that's the case, you could still resolve it into these like rectangular components, which are 90 degrees for each other. And you might call this guy here vector P sub n. It's the vector of P along the n direction. And you might call this guy here P sub t. It's the component of the vector P along the t direction. These are both still vectors because they have magnitude and direction, though they're just resolved into a different coordinate system, the n and t coordinate system, instead of the x and the y coordinate system. Okay. But the point is, I was trying to draw this vector P is the same vector in both situations. We're just sort of like resolving it into different directions, depending on maybe some orientation of a problem that we're working on. Okay. So if, again, you got like some box that's sliding up and down a ramp, maybe you want to use these normal and tangential coordinates instead of the traditional like XY coordinate system. All right. So with that in mind, we can take the vector here, P, and resolve it into these like various directions by understanding that that vector P has some magnitude in those various directions. So above here, we had the vector Px has got some magnitude generally in the x direction, and the vector Py has some magnitude here in the y direction. So we can represent the total vector P by talking about sort of the addition of the individual components that make up that vector in the x and the y directions. So if we added, let's say, the magnitude and direction in the x direction, the magnitude and direction in the y direction, we're going to get that total amount of that vector P. And one easy way that we can sort of describe the magnitude and direction of particular components of a vector is with unit vectors. Okay. So if you have a coordinate system, let's take your XY coordinate system, and you wanted to describe some component of some vector along the x direction and some component of some vector along the y direction, you might want to establish some baseline vector that you just scale with a scalar to get you that particular component. So that's what a unit vector is. So the idea here is these are imaginary vectors. I don't want to be too ethereal here. It's not like an imaginary number. It's like a vector that sort of lies on this plane in this various direction, but we'll just say imaginary for now. It's an imaginary vector used to point in a particular direction. Okay, some properties about these unit vectors. Is that in this class, we're going to align them usually along X, Y, and Z axes, but typically will be aligned in orthogonal directions. for us, that's like x, y, z is typical. Yeah. So question here in person, what does orthogonal mean? Orthogonal means that it's 90 degrees with respect to each other. Okay, so you know, one univector 90 degrees from another univector. Orthogonal, same as perpendicular. Okay, they are vectors, so they have magnitude and direction. But specifically, unit vectors have a magnitude of 1. And for x, y, and z directions, we typically use unit vectors which are denoted in this way. I hat for x direction, j hat for y direction, and k hat for z direction. All right, so if you want some picture of what this looks like, if you had some coordinate system, and let's do a full 3-dimensional coordinate system here, something like x, y, z, then the unit vectors that we're going to mostly work with in this class are vectors with a magnitude of 1 in those principal directions. So you might have this guy here, which we call I hat, this guy here, which we call j hat, and this guy here, which we call k hat. All right, so why would we want to do this? Okay, what is the point of like unit vectors? Well, they have a magnitude of 1. Okay, so if you have like, let's say, a vector that's 10 newtons in the x direction, okay, well, you can just describe that vector by saying that vector if we go in a 2-dimensional space, if you just have this vector here, let's call it P, and let's say it has a magnitude of 10 newtons. So the magnitude here of this vector P is 10 newtons. Well, if I want to sort of describe both components of this vector, which is its magnitude and its direction, I can do that by saying, okay, it has a magnitude of 10, and that's completely in the I direction. So I would just say that, okay, this vector P is 10 newtons in the I hat direction. All right, simple. The value and the magnitude of that vector is 10, and the direction in which it acts is I. All right, so it's telling you that I have 10 newtons in this x direction or the I direction. Okay, and so since this is just like a vector itself, we're multiplying this vector, which is a magnitude of 1, by 10 to tell us what's sort of occurring here. All right, now that's a very simple example where the vector is just more or less lying exactly on the x-axis, but what happens if you have a vector that's not particularly lying on that axis? Well, you can resolve the vector in space into those various directions and then write that vector in terms of its unit vectors. So let's show that here. So vectors written with unit vectors. Okay, so again, we'll go back to our classic example. We have our x and our y axis, and we have some vector out in space. Let's call it, I call it in the notes f, so I'll try to be consistent here. We'll call this the vector f. All right, and let's say that we know the angle that the vector f makes with the horizontal, and so let's call this angle here the angle theta. Okay. Now we know that we have our unit vectors that are sort of hanging out here, even though they're sort of independent of f at this point. We know that they exist, I and j. Okay, they're of magnitude 1 in our various directions, in the x direction and the y direction. So we also know that we can break down the vector f into its individual components, which we've seen this before. Here, this is like fx, and this guy is like fy. Okay, and so if we say that the vector f has magnitude this is how we typically denote magnitude, the magnitude of the vector x, and fy has magnitude, which is magnitude of the vector fy, whatever those magnitudes are. I'm just kind of keeping them as variables right now. Then we could write each one of these vectors using unit vectors. Then the following is true. The vector fy is just the magnitude of fy, whatever that magnitude is, in the j direction. Okay, that was a full definition of that vector fy. Also, same in x. The vector fx is whatever the magnitude of that vector is, magnitude of fx, multiplied by the unit vector I, which is just a vector in the x direction of magnitude 1. Altogether, then, we could use this information to fully describe the vector f. You might write it in this way, and we know from discussions last time that the vector is just the addition of this fx and this fy. So it's the addition of vector fx plus vector fy. Or if we break it down into its like unit vector composition, it is the magnitude of the vector fx in the I direction plus the magnitude of the vector fy in the j direction. Okay, and that's all that we're doing here. This would be like a full vector format of this particular guy. Okay, so we've got some magnitude of the vector in the x direction, some magnitude of the vector in the y direction, and we've just multiplied those magnitudes into the various directions and then added them together to get our full vector f. Okay. A couple of other interesting things that sort of come out of this, and this mostly is because this is just a right triangle up here, that we can determine the magnitude of f if we know the magnitudes of the individual constituents. So other information. Because we've sort of assigned I and j as orthogonal to each other, right? The x direction and y direction are 90 degrees from each other. We've made ourselves like this nifty little right triangle here, okay? So we can use some of the things that we know about right triangles to help us on our way. And so one thing that we might know is we could determine what the magnitude of the vector f is using Pythagorean theorem. So the magnitude of the vector f is just the magnitude of the x component squared plus the magnitude of the y component squared, all square rooted. All right. So this is the magnitude of the vector f. It's the square root of the sum of the squares, Pythagorean theorem. Right. We could also determine this angle theta if we knew what the magnitude of fx and fy were. And we see here that like opposite over adjacent would be the tangent function. So the tangent of this angle is just opposite over adjacent, right? So we also emerge with the following relationship. It's the magnitude of force in the y direction divided by the magnitude of the force in the x direction. Just like your triangle relationships here. It's the beauty of like working with this orthogonal relationship here. Okay. Lastly, the following information follows is that the vector fx is equal to the magnitude of f resolved into the x direction. So basically we're using a dot product here to dot the vector into the x direction. So if we wanted to resolve like the hypotenuse of this triangle into the x direction to get fx, all we would do is multiply the magnitude of this hypotenuse, right, the magnitude of this guy, by cosine of theta, and that would give you the vector in the x direction. Okay, so the vector fx is the magnitude, which is the magnitude of f cosine theta, specifically in the I direction. Okay. You may also see this written as, the magnitude of fx in the I direction. So the magnitude of the vector in the x direction is just whatever the full vector is resolved into the x direction through the cosine function. Similarly, the y direction, you have here the magnitude of the force resolved now not with cosine, but with sine. Okay. All right. Why is this helpful? All right, well, let's practice resolving one particular force into its components, and then I'll show you how we could attack that previous problem that we did with the tip-to-tail method using the unit vector method, and you will see how easy it is. How much easier it is, I should say. All right, so let's give this guy a roll. This is in your notes, and we'll post this guy here. So here's just a simple concept where we're going to try to resolve this force into components and write it in like typical vector fashion. So here we have a force of 800 newtons exerted on this bolt at A. I want to determine horizontal and vertical components and also write this force F using horizontal and vertical components with the unit vectors that are appropriate. Good? No, I'm just giving you time right now to sort of copy it. I'm going to do it. Yeah. I mean, I understand it's not that, complicated, but. Yeah, we go from like 0 to here in this class. So while it's easy, you just want to like enjoy it. All right. All right. I'll get the picture in here and we'll give it a go. Here's our example. This guy here, and we want to resolve into components fx and fy, and write in terms of unit vectors. One problem with this particular picture is that we don't have a coordinate system on here. If you're ever working with a problem and there's no coordinate system assigned, I would just say sort of assume the standard. Here it's pretty easy to understand what the standard might be, where your sort of origin of your coordinate system is centered on your particle of interest, which here is point A, and so we'll make this our coordinate system for the problem. x and y. If you draw me a picture, it's fine. Otherwise, I'm just going to kind of assume that this is your coordinate system. On an exam, I will be very clear on the coordinate system for you. Okay. There'll be no like coordinate system guessing on the exams. It's just kind of like a little bit too mean. I'm mean, but I'm not that mean. Okay. All right. So we're going to resolve this into fx and fy. All right. Well, fortunately, we've already got this like 35-degree angle given to us. So naturally, the triangle that you would immediately probably pursue in this problem looks something like this, where you've got these two components that make up this particular force. Okay, so here would be like your fx, and here would be your fy. So we just want to write what is the fx and what is the fy in terms of our unit vectors. Okay. All right. Right. So we have this 35-degree angle, so we can resolve the 800 Newton force into the x direction using that 35-degree angle. But we must notice that the force is pointed in the negative x direction. You can deal with this in a couple of ways. You can always work with the counterclockwise angle from the x direction. Here, that would be 145 degrees as your angle that you're working with in your problem. If you're doing that, you can follow this guideline directly. All right. So if you did, for instance, cosine of 135 degrees, you would get a negative value. Right? Or you can sort of resolve directly to the x-axis from here, but understand that it's pointing in the opposite direction of our traditional x-axis, so just throw in a negative sign. And I think that's the method I typically go with. Okay, so here, fx, this is the magnitude of f multiplied by cosine theta. I will say that this here is the angle theta, and this is generally in the negative I hat direction. All right, so we have a negative unit vector here, and my negative I hat is like this unit vector here, negative I hat of magnitude 1 pointed in the negative x direction. All right, so we can plug things in here. The magnitude of f is 800, so 800 newtons times cosine of my angle, which is 35 degrees, multiplied by my unit vector, negative I hat. So we'll get here that the vector fx, after resolving here, is going to be negative 655 newtons, specifically in the I direction. All right. So we have a magnitude, 655, and we have a direction, which is negative I hat. Okay. Usually, just from traditional mathematical perspective, you put a negative sign in front of the value. So this is typically how you'll see it. But really how you would read this is this vector has a magnitude of 655 newtons, and it's in the negative I hat direction. That's how you would want to like interpret this particular vector. Okay? And that sort of makes sense. It's some percentage of the total vector f, and it's pointed in the negative x direction, so we would expect a negative I occurring here, and we see that. Okay. All right, we can do a similar sort of thing with the y direction. Magnitude of f. But here now we're resolving this guy with the sign of theta. And this guy is pointed upwards, so this vector here is generally in the positive y direction, so I'm going to take my positive j hat unit vector. Okay, so this is going to be 800 newtons again, times the sine of 35 degrees, and this is in j hat. So I'll find that my component of this guy in the y direction, 459 newtons in positive j hat. So these together would be like the two vectors that make up the sides of the triangle of that full f vector. All right. So once we've sort of made our way through these guys, we can then write the full vector f in terms of its components. So this is sort of the last bit of the problem. So here, f is just going to be this fx plus fy. So here, this is going to be negative 655 I hat plus 459 j hat. And it's traditional to sort of incorporate this as one sort of value and then put your unit at the end. This is usually how it's done. So you get sort of like the full information about the directionality and the magnitude, and then the unit gets popped on at the end. It's typically how it's done. All right. If we wanted to double check ourselves and make sure that our magnitude is correct here, maybe we go through that exercise quickly. So let's check magnitude of f. Okay, it's the square root of the sum of the squares to get this particular magnitude. Okay, so here this would be negative 655 squared plus 459 squared all to the 1/2 power, so the square root of that. And if we work this, what should we get? 800. So this is just a good check for us at the end. Right. Wasn't asked for in this problem, but sometimes if you need to check your answer, it's just a good thing to try to do. Okay. All right, cool. We've learned how to resolve a vector into components. I think pretty simplistic stuff, but very powerful. And now we're going to see why it's powerful, because I want to try that example that we did last time one more time, except now we're going to do it using unit vector math. All right, sort of resolving each one of these forces into components, writing in terms of unit vectors, and then we can add them directly, and I'll show you what I mean. Okay, so this is the same sample problem that we did before with vectors q and p of 60 and 40 newtons. We drew them tip to tail last time and made that crazy triangle, and the answer that we found last time was 97.7 newtons, 35 from the horizontal. Just as a reminder for those that fell asleep yesterday. This time we're going to resolve each one of these into its components. We'll sort of put the standard coordinate system on there, the XY coordinate system. And then we can just add those two guys together directly and see what we come up with. All right. I'll bring this picture into the notes. And here I'll say use traditional vector math. All right. So let's tackle vector q first. It's obviously going to be comprised of like its magnitude of the x component in the I hat direction plus the magnitude in the y direction in j hat. So let's put our traditional coordinate system on here just to be crystal clear. And here, this is the x direction, this is the y direction. And the x direction is associated with unit vector I hat. The y direction is associated with unit vector j hat, right? Remember, we just have those like invisible unit vectors of magnitude 1 pointing in those general directions. Okay, so we can resolve this 60 Newton force that is Q into the x and the y directions by noticing that the angle that Q makes with the horizontal and the vertical is 45 degrees in both situations. So this angle theta here is 45 degrees. You can, slice it however you want. So the idea here is that in the x direction, we're going to have the magnitude of this vector Q, which is 60 newtons. We're going to resolve it into the x direction through the cosine of the angle theta. So this is cosine 45 in I hat. Plus, again, the magnitude of this force resolved into the j direction using the sine function. Those of you who are swift and adept will know that sine 45 and cosine 45 are the same. And so here the vector q, written using like this unit vector notation, is just going to be 42.4 I hat plus 42.4 j hat newtons. Okay, so that's how we would represent this vector using this sort of like rectangular components. Okay. All right, we can do a very similar thing with P. Again, thinking about like making our triangle, this triangle here. Okay. We're here now, our angle of theta is 20 degrees. So we're going to resolve P into the x direction with cosine 20 and resolve it into the y direction with sine of 20. Uh-oh. My writing pen just went out. Just like very finicky. Like I move it a little bit and it like the power cord disconnects. I need a better better method. I'll figure something out. I'm an engineer, dang it. All right. So here we're resolving that force P, just 40 newtons, into the x direction through cosine of 20 degrees. And I'm going to add to that my magnitude of P. Are you serious? I just gotta like not touch it, but if I touch it, okay. Resolving it into the y direction through the sine of 20 degrees. So here we do a little bit of algebra, and you're gonna get 37.6 I hat plus 13.7 j hat newtons. Man, it'd be sweet if like a unit was named after you, wouldn't it? You know? What would the heart unit be? A unit of punishment, probably. Okay, no, I'm just kidding. A unit of failure, such as my life. Okay, no, I'm just kidding. All right, so we got these two vectors now sort of resolved into their individual directions. And the beauty here is that we know that this guy has like 42.4 newtons in the x direction. This guy has 37.6 newtons in the x direction. So if we just add the contributions in the x together, we're going to understand what the final resultant component in the x direction will be. And if we add the two y components of these two guys together, we'll get the y component of the final vector, and we can be on our way. So what I mean by that is that the resultant force here is going to be like a summation of all of the x components. I'll just write this in words. In I hat plus the summation of like the y components j hat. Okay, so if we just do this, we know that our resultant force is going to be the force P plus the force Q. And here we have P is 42.4 I hat plus 42.4 j hat newtons plus Q, which is 37.6 I hat plus 13.7 j hat newtons. You could rearrange this to have like this guy adding with this guy. It's just like two vectors, you know, on top of each other, both in the I direction, right? And same with this guy and this guy. And you would end up with a resultant force after sort of executing both of these things. It would give you 80 I hat plus 56 j hat newtons. All right, so this is your resultant force written in terms of its unit vectors. Now, the original problem asked us to determine the magnitude and direction of this vector. If you wrote this down in this particular form on a test, if I asked you for magnitude and direction of a vector and you wrote that on your test, you're done. Okay, like that's perfectly fine in my eyes. All right. But if we wanted to go through the full gamut here, we know that the magnitude of the resultant vector is the sum of the squares, the square root of the sum of the squares of the components. So it's going to be something here like 80 newtons squared plus 56 newtons squared, all to the 1/2 power. So the magnitude of my resultant vector, if you punch this in a calculator, 97.7 newtons. It's the same as what we found using our triangulation method. Okay, so let's maybe draw what this resultant would look like then if we have some of this information. Okay, so here's like x, here is y. I've got 80 in the x, 56 in the y. All right, so if I say out here is like 80 newtons, then maybe, I don't know if I'm trying to scale this appropriately. Does that look about right? Should it go a little higher than that? Maybe a little higher than that. Maybe here's like 56 newtons. So I'm getting my vector to point at that particular location there. So here's my resultant vector, r. Where I have 80 in the I direction. That's basically this portion. And I have 56 in the y direction. That's basically this portion. Right? And I know that the magnitude of this particular resultant is 97.7 newtons. If I wanted to know this angle here, I could determine that as well. Just use your trig. Remember that tangent of your theta is the opposite over the inverse. So this is just going to be tangent inverse of 56 over 80. You work this out, you'll get an angle here of 35 degrees. This is the exact same answer that we came up with when we did that crazy like tip to tail triangle drawing and stuff and used law of sines and law of cosines and all that. Except here we're now just like sort of sticking to algebra, which is nice. Another benefit of this method is that if you have like many forces that are acting on a certain point, you don't have to try and draw like tip to tail like 50 vectors together. It'd just be a nightmare to try to like analyze where the final resultant would end up. Okay. So I think that'll be it for today. Maybe we'll do one more example tomorrow, and then we'll start in on a new topic, which is 2D equilibrium. So that's it for today. Until tomorrow.